All right, so welcome to our next unit. This is our naming compounds unit. So I'm going to go to my present mode. So we're going to get started on this set of unit notes. We are on page number, hold your thoughts. You should have a set of reference tables with you so that you can write on your reference tables and then you can refer to them. So this is the naming compounds unit, and we are on page number 92 of your, oops, I went back a little bit too far. So we are on page number 92 of your unit notes. So let me just get that jotted down over here. So page number 92 of your unit notes. And I like to change my color of pen. I feel like I'm using blue today, would be a good color choice. All right, so let's get started. So when we're writing an element's chemical formula, right, we have monatomic, which let's break apart words, right? So the prefix mono meaning one, right? One atom alone in nature. And so all elements except for 7 on the periodic table are considered monatomic, meaning one. So if you see a monatomic gas in a question, that's going to be referring to, from our periodic table unit, our group 18 noble gases. So group 18, and that would be our noble gases. So I like to throw in a little bit of review when I get a chance. So carbon, for example, is a monatomic element. Calcium. And so now the opposite of monatomic is going to be a diatomic element. So the prefix di meaning two. So the prefix di means two, a 2-atom element. So our diatomic elements are atoms that exist paired with themselves in nature. And there's a couple different ways to remember these. One of these ways is Hofbrinkel. And hydrogen, for example, is a diatomic gas. There's a couple different ways to remember that. So Hofbrinkel is one, and I also like Brinkelhof, Burr, and then Ingelhof. Sometimes I joke around and say that's David Hasselhoff's second cousin twice removed, right? It's a nice German name, Brinkelhof or Hofbrinkel. And there's another way we can remember these, which is the 7-up method using your periodic table. There are 7 diatomic elements. They form a 7, and then one of them goes up. So I will show you that in just a second. So hydrogen, for example, is a diatomic gas. So we have hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are the 7 diatomic gases. And if we're doing a particle diagram, right, we would have drawn those together like this, right? A diatomic element, 2 of the same symbols stuck together, right? So then here's 2 diatomic elements, and please do not judge my coloring and scribbling ability. All right, so fluorine is another example. So when we mean by diatomic, remember a compound is 2 or more different elements chemically combined. So this is not 2 different, so we still only have 1 capital letter. So this is still an element, cannot be decomposed by chemical means. So what did I mean by 7-up? So Hofbrinkel or Brinkelhof, right? So here is H, hydrogen. So I'm just going to put a little star there. And then Hofbrinkel, H-O-F or Brinkelhof. So I'm going to just put a little star on each of our diatomic elements here. And so remember I said that they form the number 7. There's 7 of them, so 7-up. So I'm just going to write that up here at the top, 7-up, and then Brinkelhof. Or you can do Hofbrinkel. So here's the number, the 7-up. So if I go back to here, so starting, so nitrogen, here's, sorry. So here's our 7, right? It forms the number 7. And then our hydrogen is up, so 7 up. Those are the diatomic elements. So now when we're writing a chemical compound's chemical formula, right, so we have 2 or more elements chemically combined. They're going to be made up of ions. So remember from our atomic structure and periodic table unit, an ion is a charged atom, and it acquires that charge by either losing or gaining electrons. We have cations that are positively charged because they lose electrons. And remember, they're a positive charge because they have more positive protons than negative electrons. And an anion is a negative charge because it has more negative electrons than positive protons. And so this is where those oxidation numbers on your periodic table come in, right? Because those are going to indicate our ions. So these are the charges listed on the periodic table in the upper right-hand corner. And they indicate whether an atom donates or accepts electrons when forming a compound. So if you're donating, so it's hard to find my cursor over here. If you're donating, that means lose electrons. And if you're accepting, that means it's a gain of electrons, right? So donating is losing, gaining is accepting. So now let's take a look at our oxidation states. So over here, remember we have the oxidation states are in the upper right-hand corner. And if beryllium right here is a +2, this means it'll lose 2 electrons. And over here, let's take a look at so we have our metal side of the table. So notice I was on the left, it was a metal. And now we'll go over here to our non-metal side, and over here, and it's that fluorine is a -1, so that means gain electrons. So remember, the metals lose electrons, the non-metals gain electrons. So they're going to form chemical compounds together. So let's take a look at some examples. So hydrogen is going to become the hydride ion, and it could either be a +1 or a -1. Chemists generally don't like the number 1, so if you see a plus or minus, it's plus or minus 1. And you'll notice that I changed the name to ide. So when it's an ion, it's going to end in ide. So hydrogen will become hydride. Fluorine becomes fluoride. What's in your toothpaste is sodium fluoride, which is a chemical compound, right? Where the fluorine is in the gain 1 electron. So here fluorine has gained 1 electron. And then the sodium was a +1. Sodium was the one who lost an electron. And together they formed a little happy chemical compound couple. So chromium, Cr, has multiple oxidation states. Remember, because it's a transition metal. So transition metal. So then it can either lose 2, lose 3, or lose 6. So when it forms its ion, right, which then would be the chromide ion. So what this leads us to is the IUPAC naming system. So if you see this in a question on a test or in a homework assignment, don't get worried. It's just an official way of naming chemical compounds that is international. So there's the same rules all over the world. The International Union of Pure and Applied Chemistry is what UPAC stands for. This organization determines the globally accepted rules for naming compounds. And these are the rules that we're going to be learning in this unit. So we're going to start off with a binary compound, right? So we're going to start off with the easiest ones, which are the binary compounds, composed of 2 elements, right? Because the prefix bi means 2. So a binary compound is made up of 2 elements. Remember, it has to be 2 different elements in order to make a compound. So it can be either ionic, which is a metal and a non-metal, right? So on the left side of the staircase and the right side of the staircase, right? Opposites attract. Or we can have what's called a molecular compound, which is going to be 2 non-metals. So this is going to be an important distinction as we go further on in chemistry. So let's talk about how we name our binary compounds. So to go from the chemical formula to the chemical name. So if you're given the formula and you're asked for the name, this is how you're going to take what you're given and you're going to determine the chemical name. So the compound contains 2 different elements. Like I said, it is binary. So you're going to match the first element symbol to its name and you're going to keep its name the same. So how do you know all of the the element symbols names, right, you're going to want to make sure that you're going to use table S from your reference tables because some of the elements are a little bit trickier. And then the second element, right, you're going to find the name of the second element and you're going to change its ending to "ide." Okay, so this is the ending "ide" is going to be the clue that it's in a chemical compound and not just two elements that are mixed together. Let's work through some examples. So NaBr. So the first thing I need to do is I need to know what is the name for Na and what is the name for Br. So sodium from table S. Don't always assume that you know the name. Make sure you double check on table S. And then bromine for the Br. So then now the first element keeps its name. So sodium stays sodium, right? Keeps its name. And then now since they've merged into this happy chemical compound, the bromine becomes bromide, right? So that's sodium bromide. So let's try the next one. If I have Li and O, I have to go to table S, right? You want to make sure table S is your really good friend. You're going to find Li on table S. You're going to give it its name. All right, so that's lithium. And then you're going to go and find O, which is oxygen. So lithium keeps its name, so lithium. And then oxygen becomes oxide, right? So oxide. So lithium oxide indicates that it's a chemical compound between lithium and oxygen by having the ending I. So now I have WS3. So again, you're going to check table S because W is not an element we've really seen very often yet. So that's our element tungsten. And then sulfur. And so tungsten's going to keep its name because the first element always keeps its name. And then in this case, the first element is a metal. Notice that sodium is on the left side of the periodic table. So is lithium, and so is tungsten. Bromine is on the right side of the table, non-metal, non-metal, non-metal. And so our non-metals are the ones that they're changing their names. So sulfur becomes sulfide. So now let's do another one. Now I've got K, right? That's a metal. It's over on the left-hand side of the table. Go to table S, find the symbol, get the name. Go to table S, find the symbol, get the name. I've got potassium and iodine, and that becomes potassium iodide, right? So you're going to change the last, and you're going to change the ending of the non-metal to ide, and the metal keeps its full name. So this is how we go from our chemical formula to our chemical name. And so now we're going to have to be able to learn how to write the chemical formula from the chemical name. So we're going to take the chemical name and now we're going to convert the chemical name into the chemical formula. So now you're going to match each element's name to a symbol. Again, you're going to use table S of your reference tables. Right, you're going to use table S. And you're going to look up the oxidation numbers, right? You're going to find those charges on your periodic table. And we're going to do what's called the crisscross, right? So I like to say symbols, charges, crisscross. So you're going to get an overall neutral charge. What does neutral charge? Neutral means 0. That means all the positives equal all of the negatives. And what I mean by crisscross is you're going to end up getting a subscript from those charges. So the subscripts are positive whole numbers, and we never write the subscript of 1. So when we're crisscrossing, we're only crisscrossing numbers and we're not crisscrossing the charges. This makes more sense when we go through some examples. So the order of the ions. So the first element is always going to be our positive oxidation number because it has a lower electronegativity and ionization energy. And so this is going to typically be a metal. Typically going to be a metal in our binary compounds that we're working on. The second element is going to have the negative oxidation number because it has a higher electronegativity and ionization energy. And this is typically going to be our non-metal. Right, because it has to do with the attraction for electrons, because that's what happens in a chemical bond is there's going to be a loss and gain of electrons that are going to end up together as a chemical compound, because the metal is going to lose electrons and the nonmetal is going to gain electrons, right? So lose and gain electrons to form a chemical compound. And so the ones that have the higher electronegativity are going to be the ones that gain electrons, and the ones with the lower electronegativity and the low ionization energy are going to be the ones that are going to lose the electrons. So let's look at some examples. So let's look at magnesium chloride. So I have the first thing I need to do is I need to find the symbols. And again, you want to make sure that you're using table S of your reference tables. Be very careful because magnesium and manganese are very similar. The magnesium is Mg and it has a positive 2 charge. So I got that from the periodic table, the upper right hand corner, right? So I'm going to take my symbols, I'm going to put the charges on top of the symbols, and now chlorine. And so now chlorine has more than one charge on the periodic table, but since the magnesium has to be positive, the chlorine is going to have to be negative. So we're only going to use the negative charge, so which is going to be a -1. So now I said symbols, no charges. So I have to get a +2 and a -1 to equal 0. So if I want to get these two to cancel each other out, I need 2 of these -1s to balance out the +2. So this is where that crisscross comes in. I'm going to take this 2 and I'm going to bring it down here. And I'm going to take, let me just scribble that out for now. And then this 1 is going to go down here. So I need 2 chlorines to balance out that magnesium. So then this is going to become magnesium chloride. Notice I didn't write the 1 or the negatives or positives. The subscripts in chemical formulas come from the charges, right? From this +2 and this -1. 2 -1s balance out that +2. All compounds have to have the sum of the oxidation states equal to 0. So now let's look at another one. Let's look at tungsten phosphide. Well, tungsten's kind of a weird one. We haven't used that very much. So we're going to go to table S and tungsten is W. And we're going to go and we're going to make sure we're going to go to the periodic table and we're going to get a charge for tungsten, +6. That's a big oxidation state. So now we're going to go and we're going to go phosphide. Remember, if it ends in "ide," it's going to be that non-metal. And I have to find the non-metal that looks the closest to phosphide on table S, which is going to be phosphorus. And I'm going to get the negative charge for phosphorus, which is going to be a -3. So now we talked about symbols, charges, and crisscross, right? If I have a +6 and a -3, so then I need to do, if I crisscross, I'm going to bring the 6 down here to be a subscript of 6. I'm going to bring this 3 down here to bring that to a subscript of 3. Oops, sorry about that. My writing tablet is a little bit sensitive today. Okay, so I have a 3 and a 6. So the common multiple between 3 and 6, right? So if I multiply this -3 times 2, that's going to be a +6. So I really need 2 phosphoruses to balance out that 1 tungsten. So notice how I have written over here, the smallest whole number ratio, right? Elements combine in the simplest whole number ratio. 3 and a 6, right? This is a 3:6 ratio between the tungsten and the phosphorus. That's not the smallest whole number ratio. So I need that to become a 1:2 ratio because these are both divisible by 2, right? So this is a 1:2 ratio. So if I go back and I put those charges on top, right? A +6 and a -3. It means I have 2 times a -3 is -6. And then that cancels out the +6, right? So when I add these two things up together, the sum of the charges is equal to 0. So just double checking to see where we are. Okay, we're almost there. This is going to be our last example. So now let's look for yttrium sulfide. So remember, we're going to find table S. We're going to find because our first element always just keeps its full name. So we're going to find the symbol for yttrium. Then we're going to find the symbol that looks closest to sulfide on table S, which is going to be our sulfur. So we're going to have Y for yttrium, and we're going to have a +3 charge because we're going to get that from the periodic table. Symbols, charges, crisscross, right? I'm going to write those steps up here, up at the top. So step 1, you want to make sure you get your symbols. Step 2, you want to get your charges, right? Where do symbols come from? Symbols come from our periodic table, or table S. Where do we get our charges from? We get our charges from the periodic table, right? Those are the oxidation numbers. And then our last step is going to be crisscross, right? And then, right, which is going to be to give us the ratio that we need. We're going to crisscross. We're going to bring the charges down to the opposite side to get a subscript. And then we're going to have to possibly reduce if we have, if it can be divided by the same number. So sulfur is a -2. So when I crisscross these, I'm going to take the 3, I'm going to bring the 3 down here. I'm going to take this 2, I'm going to bring the 2 down here. Because now if I look at my charges, I have 2 times a +3 is a +6, and I have a 3 times a -2, which is a -6. So a +6 plus -6 equals 0, so I have a valid chemical compound. So then that's going to be Y2S3. And then that's going to wrap up our binary compounds. In our next lesson, we're going to learn about how to name elements that have 3 or more elements in their compound. All right, so make sure you practice and review.